All right, so let's get started talking about things that are probably actually a lot more familiar to you, at least from how we're used to handling things from, say, statics or mechanics of materials perspective. We haven't talked a ton about stress, and we've kind of used stress as something we thought of as part of the strain energy. We had the integral of stress times strain, but we kind of made some approximate approximations for what we would take for our stress there. And it turns out you can learn a lot that way. So what did we do is we focused primarily on one-dimensional objects, bars, which I think can seem kind of dull, but as we talked about earlier, if you look around you, a lot of what you're seeing are structures constructed of rods, plates, and shells. Like you're sitting on a chair that's a plate that is being supported by rods. The rods in here are railings that are horizontal spans with vertical trusses, the beams running across your ceiling, the columns holding up this building. These blackboards are plates. This table is a plate sitting on rods. So these one-dimensional and two-dimensional objects, A, are all around us, and B, they allow us to simplify the complexities of the math such that we can actually solve some of these problems and gain some intuition for, like, okay, where is the stress going to be large? Where is this thing going to bend a lot? Those types of questions. The true, say, field equations of solid mechanics involve four components, and you might have heard these talked about in mechanics of materials as well, but we probably talked about them a little bit differently. And so the equations of solid mechanics have to any object in equilibrium has to satisfy these four sets of equations. And the first one are equilibrium equations, and that's going to be our focus for today. And these equilibrium equations are in the same spirit as what you learned in statics way back when, in which what we're trying to accomplish is make sure that a body in equilibrium, all the forces in all the different directions should add up and cancel each other out. Otherwise, this thing would be moving or spinning. So we kind of associate equilibrium with, in statics, we think about it as the sum of all the forces equal to zero. And then in mechanics of materials, what we say is, well, actually, for an elastic object that can deform, really what you want to do is look at the force relative to some cross-sectional area, which is going to give you a stress in that body. And the stress is really the fundamental entity describing that object. Why is it the fundamental entity? Because the stress gives you markers for, if you exceed a certain threshold, this thing will break. It's a material property. The stress is proportional. Think about the units of stress are pascals. The stress is proportional to the elastic modulus, units of pascals. Proportional to the shear modulus, units of pascals. So stress is kind of this fundamental quantity that describes what an object or a three-dimensional body is experiencing. And what we do in mechanics of materials is we average over some amount of space. And that leads to equations for stress that are algebraic. Just force over area, or moment times y over second moment of area. Torque times rho over second moment of area in polar coordinates. Transverse shear stress, the shear force times the first moment of area over the second moment of area times whatever width of your object that you're looking at. Those equations are all tricky You have to identify what all the components are in there, but they're algebraic. And that algebraic form of these equations for the stress in a body comes from the fact that we're saying, like, well, let's just assume that there's not much variation from this side of the object to this other side of the object. That, in general, is not true. And in reality, stress varies throughout your structure in all directions. You see this if you've ever worked with SolidWorks or COMSOL or any sort of finite element simulation where you kind of are deforming the structure and having it kind of overlay a color plot of the stress within that structure. That stress is varying. Your rainbow colors are going from blue to red at different points, depending on which way you look at it. And this is important because we need to be able to compare the stress that this body is experiencing at any point to, for instance, the maximum stress before it's going to break. So you can answer questions like, if I sit on this table, will it break? If it's going to break, where is it going to break? Knowing that allows us to reinforce an object. So that way we say, okay, here's the weak point. Here's where the stress is concentrating in the higher quantities. We need to engineer around the fact that that's where this thing wants to fail. And so these equilibrium equations, as you'll see shortly, turn out to be differential equations. And they're differential equations because at each point, as you move from one side of the object to another, the stress varies just a little bit. And that variation, as you move in one direction, that's what a derivative is telling us. How is this quantity changing as I move in this direction? How is this quantity changing as I move in that direction? And the tricky thing about stress, as you might recall, is that stress is a tensor. And tensors are hard. A lot of physical quantities are vectors, and we're kind of familiar with vectors. We draw arrows. They have components in X, Y, and Z. But stress is hard, and solid mechanics in general is hard for two reasons. One, the governing equations are differential equations. That's true for most field equations in physics and mechanics engineering. But two, and this is a bit different compared to most of the field equations, is that our stress, which is described by differential equations, the quantity that we're taking different derivatives of is a tensor. And that makes things tricky. We end up spending a lot of time trying to understand things like stress transformations, which you might recall. We're going to go over that again a little bit here. We talk about things like principal stresses. Principal stresses arise from the fact that it's not obvious when you look at a tensor, what's the largest amount of stress and in what direction. So these are all tools that are going to help us answer these questions. So we need four sets of things. One is equilibrium equations, and this is describing how does stress vary in a, let's say, a body. The second set of equations, we've kind of already seen that these are differential equations. We've solved the equation for the deflection of a bar when you pull on it. And you've derived, but we didn't solve, but in your last homework, you derived the equations of a bar as being stretched and loaded transversely so that it'll bend. And what you saw is that the equations that describe the deformation of that object are also differential equations. These are broadly referred to as the kinematic equations. Again, just like with stress, we don't think about force, we think about force relative to some area that it's acting on. And just like for strain, we don't think about displacement, we think about displacement relative to some initial length. How much has an object changed shape? The third set of equations is probably the one that is least commonly used explicitly. Like if you're sitting down to do a calculation, it's often one that is less consequential than others. It's almost kind of satisfied in the background, or it's satisfied through certain things that you do computationally, for instance. But it arises from a problem, and I'm going to repeat this in a couple of days when we get to it, but it arises from a problem in which there are, for instance, in 3D, there are displacements in 3 directions, x, y, and z. But their strain, just like stress, is also a tensor. So that means strain has, it's a 3 by 3 tensor, so it's got 9 components. And due to symmetries, only 6 of them are unique. But there's a problem there. You have 3 dimensions of displacement and 6 possible values for strain. And so this problem, the problem can be stated as there are lots of non-physical strains that would solve your equation mathematically. Meaning you can, because there are 6 possible strain components and only 3 true displacements, that discrepancy leads there to be a certain number of values for strain that will solve your equation. Your math will work out fine, but will lead to something completely unphysical. That means the most obvious example of an unphysical strain is 2 material points occupying the same point in space. That doesn't make any sense. Like, how could 2 points be like overlapping? There's atoms there. That doesn't make any sense. But there are circumstances in which that'll solve the equations. And so what do you do? Another thing, and this is distinct from the problem of fracture, but you could also have a scenario where you start to pull on a bar, and solutions to pulling on this bar are that holes just pop up and disappear kind of randomly as you pull on this. That's not physical. That never doesn't happen. That's not something that could ever happen. But it is a scenario that can solve the equations. And so what you need to do is satisfy a set of equations that say we're not going to let holes randomly appear. We're not going to let 2 material points live in the same space. There has to be some rule that tells us what strains are allowed and what strains are just fictitious and fake. These are the equations of least consequence for us, and so we will not spend a ton of time on them, but you should be aware of them. These are called the compatibility equations. The fourth one, though, is important, and it's also one that you're familiar with. So the idea to close this problem, we have forces cause stress in a body. We know that stress somehow causes displacement or strain in this object, but we need some way of telling us how does stress cause strain. How does strain generate stress? There's got to be some sort of connection between stress and strain. These are referred to as your constitutive equations. And these tell us how does stress relate to strain. Hooke's law, right? You're familiar with it. It's stress is Young's modulus times strain. Except because these are tensors, we have to take a little bit more care in describing how Hooke's law looks. And because various materials are not following the same assumptions we made in mechanics of materials, we made assumptions like, oh, we're going to assume that everything is homogeneous and isotropic. You probably heard someone say this when you were taking that class, and you just kind of ignore it, or you just kind of write it down, and then it never ends up mattering later. But it matters because, for instance, the tissues in your body can be modeled using the exact equations we're going to be going through in this class, except the tissues in your body behave differently if you pull them in one direction versus pulling them in another direction. There's collagen fibers running through there that give a extra stiffness in one direction relative to another direction. So you need a way of accounting for the fact that pulling on this body in one direction is different than pulling on it in another. A huge proportion of the aerospace industry, aerospace structures, are composites, often composite laminates. And what that means is you take something like carbon fiber or fiberglass, which are kind of woven fabrics, and you immerse them in some sort of matrix like epoxy. And what you end up with is a really stiff, really strong, lightweight composite material. But because those fibers are running in there, just like the fibers of collagen in your biological tissues, that structure is going to behave differently when you pull on it in the direction of the fibers than if you were to pull on it at some angle, like say 45 degrees away from the fibers. This is what's referred to as anisotropy. The behavior of that structure depends on the direction in which you pull on it, which means that the stress that you generate in that body depends on the direction that you pull on it. There's going to have a different stiffness in one direction than it is in a different direction. So because of that, these constitutive relations that we're familiar with, Hooke's law, has to be kind of generalized to allow for the fact that things might not be the same in every direction. Almost all biological structures have some degree of anisotropy. You take a 2x4, a piece of wood from the hardware store, and the grains run in one direction along this board. That board is going to flex differently in the direction that the grains are running than if you were to go orthogonal to the direction the grains are running. If you've ever seen a butcher block table, a big wooden table that you cut up food on. The butcher block table is made from the ends of pieces of wood. So you got your 2x4, you take it and you flip it vertically. So you're looking at kind of the end of it, and you glue a bunch of those ends together. That end is so tough that you can kind of constantly be chopping at that thing with a knife, and you're hitting all the ends of the grains of wood, and it's so much stronger than if you were to hit the wood kind of on the actual edge of the 2x4. It's due to the anisotropy in that wood. The orientation of the fibers gives you something that is incredibly tough. You can use it as a chopping block for hundreds of years. If you orient and flip everything, that wood is significantly weaker when you're trying to say saw against the grain of the fibers. So these things really play a huge role in describing how different materials behave in different configurations. These concepts here: equilibrium, kinematic, compatibility, constitutive. These describe the solving these equations allows you to kind of solve a solid mechanics problem. If you're asking for how much stress is this body going to take, how much is it going to deform, is this thing going to break, is this thing going to fit when I kind of form mold it into my object. These are the equations that we're trying to solve. And this will be what we spend a little bit of time on. for the next stretch here. We're going to start with equilibrium equations and then work our way down towards the constitutive relationships. And as you'll see, unlike what we did in mechanics of materials, to do this properly means that we end up having to look at a series of differential equations that kind of will describe the mechanics of a solid object. Questions? How does this sound, all right? So how do we visualize? Let's start with our equilibrium equations. That's going to be the focus of today, is up here. And how do we think about variations of stress in the body? Depends a little bit on if you prefer the mechanics of the statics kind of approach or the very mathematical physics kind of approach. They're equivalent, doesn't really matter. But what we can do is we can say, let's look at a slice of an object. Oh, that's a terrible line. So I'm going to draw my coordinate system. I will say this is my x direction. This is my y direction. We're going to consider a thin element. So imagine that this object I'm drawing here is incredibly thin. It's like the thickness of a sheet of paper. In the limit that this object is really thin, what we can do is we can assume that it's in a state of plane stress. Let me explain what that means. I finish coloring sort of in between the lines here. Bigger one. All right. So here's our object. It's a square. It's really thin inside into the board. And what we do is when you have an object that's really thin, this is true actually in the modeling of most plates and shells. What people do is they say, well, if it's so thin, can there really be much of a change in stress in the z direction, the direction into the board? That distance is incredibly small. So we'll assume that the stress within that thickness doesn't vary. What this does is it takes our stress. So let's recall that our stress is a tensor. Usually we write this with indices below it. These indices take on Latin letters of I and J. We're going to talk a bit about initial notation in a little bit. But for now, I just want you to know that I and J and any other Greek letter, I'm sorry, any other Latin letter, K, whatever, can be within the set of numbers 1, 2, and 3, which is kind of doesn't really help us too much. But if you map in your head 1 to x, 2 to y, and 3 to z, then what that means is that you can have quantities like sigma 1, 2, which would be sigma xy, which would be like a shear stress, right? Because it's stress in one direction, stress in another direction. So you put all this together, and what you get is a tensor in which we could write sigma xx. It's terrible. Sigma yy and sigma zz. Those are stresses, those are normal stresses. Those are stresses in the x direction, the y direction, and the z direction. Normal stresses relate to normal strains, which relate to Young's elastic modulus. How much force does it take to stretch or compress my object? Right? Your elastic modulus is a measure of how hard it is to extend or compress an object while keeping the same general shape. If it starts off as a rectangle, it ends up as a rectangle, just a little bit stretched. The off-diagonal components of this thing, so this would be xx, this is going to be xy, this is going to be xz, and then we can go down here a little bit, this is going to be yz. The off-diagonal components, in which you have two different indices, are your shear stresses. Now these objects relate to your shear strains, which relate to your shear modulus, and your shear stresses, shear strains, and shear modulus describe actions that distort a shape. How hard is it to change the shape of this rectangle to a parallelepiped? Your normal stresses talk about stretching and compressing. Your shear stresses talk about distorting. Now, I'm sure you did this in mechanics of materials, but the nice thing about the stress tensor, one of the few, is that it is symmetric, which means if you have a shear stress in the xy direction, then this thing here, which wants to be sigma yx, has to be equal to sigma xy. I'll write it in like a slightly different color. I can show you why this has to be the case mathematically, but I don't think that really helps. What I'll do is I'll tell you why this has to be the case, which is that if sigma xy doesn't equal sigma yx, then your body is going to rotate, like it's going to spin. Because there's more shear stress trying to push it this way and less trying to push it this way, so it's not in equilibrium, so it's going to have to rotate. We don't deal with rotations when we're talking about objects in static equilibrium. We're looking at how these stresses balance and then deform an object. So if you're stressing it this way here, there has to be a counter stress, shear stress down here, shearing this object. Same for here, same for here. Otherwise, your object spins. Same thing is true for if you have an object and you're pulling on it. You don't have an equal and opposite force on there, this thing's going to translate. We want to get rid of translations. We want to get rid of rotations. We want to see how stresses act to deform objects. Okay, so this is the stress tensor. This initial notation is really annoying and confusing at first, but there's kind of two ways you can approach it. One, you should probably know it because that's how all the equations are written. If you ever end up going and doing something involving structural mechanics, you're going to see them written in this kind of compact notation. But two, what you end up with all these things are just like rows of equations that all kind of say the same thing. And this notation here, this stuff, helps you kind of collect them all into one compact little thing that's basically trying to tell you, you can unpack this to solve it however you need to, but really all you're looking at is like, this is how the stress changes in whatever direction you're moving. It's kind of hard to appreciate but I want to show it to you because this is how people write these equations. So if you ever open up a textbook, you're going to see it written with this notation. Okay. So the things we're familiar with, let me first point out, here's our object. Oh, I forgot, this is why I started this whole thing. We're drawing this really, really thin object. And this is just to help us for a second. Like we could do it all in 3D, it's just who wants to draw cubes and have things going in all directions. We're just gonna do it in 2D to make our lives easier. And when you have something in 2D that's really thin, what you say is, well, really, how much stress can this object really have varying through the thickness? Probably none. The thickness is so small. And so what you end up doing is making the assumption that your object is in a state of plane stress. Plane in the sense that you've taken your 3D thing that's really 3D in real life, like a sheet of paper, and you said, well, it's so thin that we'll just treat it like a plane, like a literal 2D, two-dimensional surface. And what that means is that anything that has to do with z is gone. We're going to say it's 0. And so your stress tensor changes from something that's 3D to something that's 2D. So you end up with, and we dealt with this a lot in mechanics of materials. This is how we handled all the stress transformation and principal stresses. We did everything in 2D because it's a lot easier. 3D is a little bit more complicated, but I'll try to make it easier for you as well in this. Okay. Here's our object. It's in XY coordinates. We're going to call this the origin. And just like we're used to in a mechanics of materials setting, we will say that there are stresses, which are forces acting over some area here. I should probably give you some dimensions here. So let's say that this length is some kind of infinitesimal length in the y direction. We'll call it dy. And this length will be dx. Technically, what we would do is say that the distance in the z direction is our unit distance. We would say dz is equal to 1, but we don't need to worry about that for right now. Okay, so we have dy dx. If we apply a force on this face, if we apply a force in the x direction, then that should generate a stress in the x direction. Now, that force is going to be divided by the area, which means it's going to be divided by dy. That's the area that it's facing. And it should be divided by our dz. We said dz is 1. So it's kind of like force over dy times dz is our stress. And we'll call that the stress in the xx direction. It's xx because it is in the direction of the x-axis, and it is, how do I say this? I always forget which order is which. Oh. I forget exactly. I forget what it's like. Which order is it on, and then which? It doesn't matter. This is going to be our x-x direction here. So this is sigma xx because it's along the x-axis. And we could have a stress in the y direction, which is going to be our sigma y. It's a normal. These are our two normal stresses because they're acting orthogonal or normal to the to the surface that they're acting on. We also have shear stresses. Those shear stresses are going to be acting parallel to the surface that they're acting on. So it's going to be some force in this direction divided by that same cross-sectional area, dy times dz, where dz is equal to 1. This is our xy. And we know there has to be an equal force down here of sigma xy. Otherwise, this object would, if this wasn't here, this object would spin. We could say that this thing is also in the presence of body forces. Body forces act on the volume of the object. You should think of a body force as being something like gravity or a magnetic force, which is acting essentially uniformly on the entire body. So we'll draw those kind of at the center of this object to indicate that it's not something acting on an edge, which you often refer to as like a traction force, something that's acting on a surface. A body force is acting on the body, so you kind of draw it essentially where the center of mass is on the object. And this would have direction, force in the y direction. You can also have force in the x direction and the z direction, of course. So the tricky thing is here. Here's the part that's weird. And I found this confusing when I first saw it until someone showed it to me as a Taylor series expansion about the stress over here. So if you're saying this is your origin, then we know that in general, a Taylor series will tell us that I could start at the point that I'm interested in. Let's see. And write this as, I'm going to have something that's like, oops. So if I want to do a Taylor series expansion around the point A, then I would say, well, I have f of A, and then I can add to that f prime at A over 1 factorial times x minus A plus f double prime And so what this means is that if you have some function, for instance, like a stress, then what you can do is you can start at the point where you know that stress value, say the origin. And you can say, how is this stress going to vary as I move away from the origin? And I can think of that as a Taylor series expansion and saying, okay, my stress at the origin is this. As I move away from the origin to some other distance, dx, then my stress is going to change in some amount. It's going to change by a derivative of that stress with respect, in this case, it's just respect to x. But in our case, it's going to be the change in that stress with respect to whichever direction we're moving in. So what does that mean? It means if I was to go from here, this face, to this face, I've moved a distance dx. And therefore, my stress over here should be, let's look at our Taylor series expansion. The original stress plus some first order variation in that stress. And this is all we use here. We kind of say everything else here is higher order terms. or order x minus a squared. So we end up using just this kind of first term to see how our stress is varying. How does that work? Why don't you need all the terms? Why don't you need the second term? Well, the idea being that if dx is kind of infinitesimally small, then you should always be able to just kind of take the stress you have at a point, move a tiny distance away, and then figure out how that stress has changed as you move that tiny distance. And since that distance is so small, squaring or cubing or taking that to the fourth power is basically adding kind of 0 to it. So the end result is we have something that's like the stress that we had originally, so sigma xx, plus the derivative of that stress times where we are minus where we were. So the derivative of that stress is unfortunately no longer an ordinary derivative because we are now able to take derivatives in whichever direction we go. We could take a derivative in the x direction if we move an x, or we could take a derivative in the y direction or the z direction. So this becomes a partial derivative. So this is kind of the partial derivative equivalent of this term here. Now we have to multiply that by where we are minus where we were. If we were at the origin and we've only moved in the x direction at a distance dx, then dx minus 0 is just dx. So we can write this as the kind of change in stress in the x direction times dx. Take a second and see if you can fill in the other three. All right. Let's see if we can check your work with mine. The top one should be pretty straightforward. This one should give you sigma yy plus the partial derivative of sigma yy over dy times the distance we've moved, which was dy. The other two are perhaps a little bit trickier. Let me start with this one. This one's going to be sigma xy plus the partial derivative of sigma xy divided by dy times d. Oops, which way did I go? Sorry. I messed it up. Can't read my notes. So we've moved from here to here. Dx. And then this top one will be sigma xy plus the partial derivative of sigma xy dy. This can be kind of confusing. You might be thinking to yourself, well, wait a minute. I mean, you kind of moved from like way down here to way up here. So why did you get to just pick dx and not dy for this one? And the reason is that this is just kind of the problem with the way we schematicize these things. This line here is really a shear stress that's running all along this face here. So in reality, it's not just in this top right-hand corner. I just kind of drew it there. That's how we draw this. In reality, this shear stress acts on this entire face. So even though it looks like we moved diagonally up to go from here to here, really what we did is we went from here to here. We just moved in the x direction, which is why this thing has a variation in the x direction. Same for up here as well. Folks get something similar? Now we're going to do what we always do to find the equations of equilibrium. We just sum the forces in our given cardinal directions and set the summation equal to 0. We'll do it in just one direction, and the results will all be the same in the other ones. So yeah, let's do that now. Okay, so before we do our summation here, let's point out a couple things. This direction and this direction and this direction and these directions are all positive x and positive y. So we'll just do this in x, and we'll say to find our equilibrium equations, the same rules always apply, which is that the sum of the forces in some ith direction should equal 0. Again, I could be 1, 2, or 3, meaning in this case in Cartesian coordinates that I could be x, y, and z. So we will sum the forces in x. We've basically drawn a very fancy free body diagram. So we'll sum the forces in x and set them equal to 0. And what that means is that, first I want to back up just a quick second and say, even though kind of principally we really care about stress, the rules of equilibrium still tell us that the sum of the forces in our object should equal 0. So we're dealing with stress on our free body diagram, but we need to sum forces. So what that means is we need to take our stress value So for instance, something like this, and multiply that by the cross-sectional area that it acts on to give us a force. I'm going to do this with dz in there. Even though I said dz was 1, I find it confusing when I look back at my notes to remember that dz was 1. So we'll just do it with dz in there. It's not going to matter. So we'll sum the forces and set that equals 0. And what that means is that we'll take first off this one up here. It's positive. So we'll write sigma xx plus the partial derivative of sigma xx with respect to x times dx. Now that's a stress. We take that thing and multiply it by the area that it acts on. The area that it acts on is dy times into the board dz. Now the equal and opposite force over here to this one. What color should we go with for that? We'll go with blue over here. This will be negative. These ones are negative. So those are going in the opposite direction, so we need to subtract off sigma xx times dy dz. We now need to handle our shear stress in the x direction, which is, I should probably circle the ones I'm actually using here, right? So we are using this one, and this one, and this one. Those are the only ones acting in the x direction. So we'll have to add to that our shear stress multiplied by its area. So this is going to be sigma xy plus the partial derivative of sigma xy with respect to sigma y, with respect to y, times dy. Now, as you notice, this one is acting on the area element dx times dz. And finally, we have, well, actually not finally, we have two more. We have sigma xy times dx dz. That's for this one. And lastly, we also have a body force acting in the x direction. This is a body force. It acts on the volume of the object. So this is a body force has units of force per volume. So if you need a force balance, what you need to do is take that body force and multiply it by the volume element. And so that means we're going to add f of x times dx dy dz. And all that thing is going to equal 0. Good? Yeah? All right. All right, this looks terrible, but it's not that bad. We're going to simplify. All right, how do we simplify? The first things first is we can identify that some stuff is going to go away here. So for instance, let us look at this quantity, which multiplies these, and this quantity. They cancel each other out. Great. This quantity, which multiplies this, is the opposite of this quantity. So they cancel each other out. We're left with dxx dx Now you'll notice that each of the differentials in this equation multiply dx, dy, dz. And all of those things add up to equal 0, which means we could factor out the dx, dy, dz, and we could actually say it goes away. It moves to the other side, which is equal to 0. So these things disappear. So in 2D, plane stress, our equilibrium equations becomes simply the partial derivative of the normal stress in the x direction plus the partial derivative of the normal stress in the y direction plus the body force in the x direction is equal to 0. You can probably guess if we were to do the force balance in the y direction, what the result would be. What do you think it's going to be? Take a second. This is where, because of these patterns, this is why the initial notation is really useful, because these equations all kind of look the same. All right, what do we think the equation looks like if we were to do this force balance in the y direction? It's probably going to look like sigma yy dy plus sigma xy dx plus the body force in the y direction equals 0. Right? Pretty straightforward. Questions? All right, why don't you think of some questions while we take a break until 10:08. Okay. So we did this all in 2D, mainly because it's easier to draw and visualize what's happening on a plane. Not for any physical reason. We don't need to do this in 2D. It's just easier to see all of this kind of chicken scratch on a 2D plane than it is to draw this on a 3D cube. But we've already seen how by doing this force balance, we kind of could guess what the form of the force balance in the other direction is. And likewise, we can kind of guess, not really guess, if you were to do this force balance in 3D, what you would get is 3 equations. So we did it in 2D, we got 2 equations, one for x, one for y. If we're going to do this in 3D, we would get 3 equations, one for x, one for y, one for z. And you could kind of guess how these equations would change. We're going to need something that describes, for instance, xz changing, the shear force in the xz direction relative to changes in the z direction. Right, we have shear xy relative to changes in y. We're going to need something that's like shear xz relative to changes in z. And you can kind of do that for all of this. So, well, in this case here, I'm going to have something that's going to be like yz, which has a change in z. And in the last case, I'm going to have some term that's going to be like a normal stress in the z direction relative to the change in the z direction. So you can kind of guess what the form of these equations are going to look like. If you don't want to guess, you could do this whole force balance out on a cube and you'll get to the same result. But in 3D, our equilibrium equations follow the same pattern. And what they look like is this. They look like the partial derivative of your stress in the x direction with respect to x plus partial shear xy plus partial shear in the xz to be clear, that's f sub x, not f times x. Right, that's that kind of, I mean, it's just kind of pattern recognition gets us there. Again, you can derive this out by hand. This is one of them. Second one. Looks like that. What happened to my equal sign there? So, and you could probably guess the third one. We're following a pretty clear pattern here. Take the normal stress divided by the direction that the normal stress is acting in and add to it the shear stresses. Whoa. And if this pattern is not very clear to you, what you can see is I kind of have these things matching.
Professor Holmes, I have a question.
Yep.
So in the top two, like there's dx, dy, dz, like in the denominator or whatever, and then in the last one it's dz,
Oh,
dx, dz. So like,
because I messed up.
I cool. Appreciate it.
So I just threw that in there to make sure everyone was paying attention, right? Pattern recognition. I'm just kidding. I mess up all the time. So you can kind of see this pattern, right? This is the x direction one. Each term has x. This is the y one. This would result from a force balance in y. This would result from a force balance in z. Right? Does this look familiar? Does this form of an equation look familiar to you? In particular, what I mean by that are these terms. Think about what you might recall from like multivariate calculus. What are the operations you can do for multivariate on vectors? It's vectors and scalars. Does that look familiar to anyone? Nothing? Ah, so close, Liam. So close. What's the other one that's kind of like a gradient? Nothing? No one's got it.
It's there. It's just don't remember the name, but it's there.
This is a divergence. So you can write this a couple different ways. If you want to write this compactly, you can write this depending, I don't know how you saw it. You've probably either seen it like div stress, or the way I prefer it is a little bit more symbolically, where you take the nabla operator, which is your upside down triangle, you dot it into your stress tensor, right? The divergence of stress. So therefore, these equations can be written compactly in two different ways. There's two different types of notation people use in solid mechanics. One is called direct notation, which is like this stuff down here. And one is called indicial notation, which is when you have all these indices floating around, like this stuff up here. We could get into a long debate on the merits of both of these things. This causes great arguments in various corners of the academy. I prefer additional notation, so doesn't really matter though. So we can write this set of equations. There's 3 equations here. We can write them as one incredibly compact equation if we just write the divergence of our stress tensor plus our force vector equals 0. Now you might see this written a couple of different ways. You might see this written with lines over the objects to indicate that one's a vector and one's a tensor. So you might see something like this is a vector and this is a tensor. The other way you can write this, and we're going to come back to talking about the divergence stuff in a second, because I think there's something that can be really helpful to you there. The other way we can write this, this is in a direct notation. The other way we can write this in additional notation. First, we'll say, well, I know that stress could be sigma ij, where I could either be x, y, or z. J could either be x, y, or z. So I could write this as partial derivative of ij with respect to dx I plus f I equals 0. That probably looks a little less that probably looks like, what on earth do I do with that equation? And what you do with that equation is you start by saying, well, I know that I can be x, y, or z. So I could write this as, because I can be x, y, or z, this equation is going to be like sigma I, sigma. Oh, yeah, I should probably tell you something. Hold on. We'll let xi is going to be x1, x2, x3, which in Cartesian coordinates means x, y, and z. And so now what you do when you deal with something in additional notation is there's kind of 3 steps. This is the first step, saying that this thing is going to be 1, 2, or 3. And then the second step is saying, well, what on earth does x1, x2, and x3 mean? Why would you write something like that? That seems kind of annoying. Well, the reason you do it is because these equations, when you write it in either of these forms, the purpose for writing it in these forms here is that they don't care if you're in Cartesian, spherical, polar, cylindrical, Gauss normal coordinates, pick your flavor of coordinates. The equations are general when you are mapping them into your particular basis. And that's at that point you kind of can choose what the divergence looks like in various forms. So this is step 1, is kind of saying, all right, what does that mean? Step 2 is this is what's referred to as Einstein's summation notation. And what Einstein got sick of doing was writing a sum from 1 to 3 all the time in all the equations. And so what he said was, well, with this notation, anytime you see the same index appearing twice in the same term, so for instance, here and here, then what you do is you sum over all the i's. You sum. What does that mean you sum? Well, there's three options. There's going to be I1, 2, and 3. So you're going to sum over 1, 2, and 3. So this notation is really compact, and what it means is you start to unpack it. You say, well, this could be like sigma x, so sorry, the partial derivative of sigma xj dx. I'm going to have partial derivative of sigma yj y, partial derivative of sigma zj dz. But now I need to actually, j can be 1, 2, or 3, so I'm going to add up and say, well, this is going to be like sigma x, 1 is x, dx. Did I do this wrong? I did do it wrong. Haha, I knew it. Shit. All right, hold on, everybody. I need to fix my screen. I was wondering why this is all backwards. Sorry. Hold on. Let me see what I can do here. I messed up. Sloppy. It's supposed to be dxj. There we go. That makes more sense. All right. So let me explain this again. Pretend to delete everything in your brain that I just said. The Einstein summation rule still holds. You're going to sum over the term that has the index appearing twice in it. This free index I is either 1, 2, or 3. That tells you how many equations you have. If you're in 3D, I goes 1, 2, and 3. This tells me I'm going to have 3 equations. 3 equations. One for I is equal to 1 or x, one for I is equal to 2 or y, and one for I is equal to 3 or j. So let me try this again, but maybe try this without messing up this time. So it looks like sigma I x dx plus sigma I y dy plus sigma I z dz plus f I. So I'm going to get this equation 3 times. Once when I is equal to x, once when I is equal to y, and once when I is equal to z. And look, this equation here is these 3 equations. Just if I put in I is equal to x, I get this one. If I put in I is equal to y, I get this one. If I put in I is equal to z, I get this one. I probably just unnecessarily confused you. I mainly want you to see that we often use this compact notation in solid mechanics. And actually it gets even more compact because people say, let's write the partial xi, sorry, xj. With a comma. So if I haven't annoyed you already, this will surely do it. So oftentimes the way you'll see this equation is sigma ij comma j plus fi equals 0. These equations are identical, even though they don't look it, and they are the equilibrium equations of a solid body. If you don't like them in this compact form, remember in your head that if you're in 3D, you're going to have 3 equations. If you're in 2D, you're going to have 2 equations. 1D, 1 equation. And those equations look like this. Let's talk for a second about the idea of a divergence, because I feel like this is something that can, if you can remember this, it can really help you look at equations and make sense of them fairly quickly. I like to think of kind of your divergence and your gradients as operators that take you either up a level or down a level. What do I mean by that? So our levels are, this is a brief aside. If you're really awesome at multivariate calculus, then you can tune out for a second. I like to imagine these things as we have a couple of levels. We have a level of a scalar, which is just a number. We have the level of a vector, which is something that has kind of direction in, say, X, Y, and Z. And a tensor, which is what we've been doing with these stress tensors, which are kind of matrices, if you will. It's kind of a square rectangle problem. A tensor is a matrix, but a matrix is not necessarily a tensor. If these are your options, we could say, not that we could say, this is true. We could say that a tensor that we're used to, like the stress tensor, is a second order tensor. A vector is a first order tensor. And a scalar is a zeroth order tensor. There are third and fourth order tensors, so you could keep going as long as you would like. But the important part is just seeing this kind of sequence here. Zeroth to first to second. And here's where the multivariate stuff comes in. A gradient takes whatever object you give it and levels it up. If you take, so temperature is a scalar. If you take the gradient of temperature, you get a vector field. Displacement is a vector. It's got a quantity and a direction. If you take the gradient of a displacement vector, you get a tensor, the strain tensor. So the gradient takes whatever thing you give it and spits out a higher level of it. Gradient of a scalar is a vector. Gradient of a vector is a tensor. Gradient of temperature is a vector field, telling you how the temperature is varying across the room. So a gradient takes you this way. Divergence takes you back. So if you take the divergence of a vector, you get a scalar. You take the divergence of a tensor, you get a vector. And now you can see why our equations of equilibrium are the way they are. Because we have to add like things to like things, which means I'm adding something which looks really horrendous to F, which is just definitely a force vector. So if I take the divergence of a tensor, I know that I'm going to move this way from tensor to vector land. A divergence of our stress tensor is going to give me a vector, and then I'm adding vector plus vector equals 0. And our equation is happy. This operation on our stress tensor gives me a vector, and then I add up my vectors, and I can add things that are the same, and I get the same result back. There's one more on here. Well, actually, there's two more I can do. This is not really going to help us for right now, but it might be useful to you in the future. The Laplacian. And remember, did you cover Laplacians? And you probably encountered these. Laplacian is the divergence of a gradient. So what does that do? What does the Laplacian spit out for you? If the Laplacian is the divergence of a gradient, that means you first start with a gradient. So you give the Laplacian let's say we give the Laplacian a scalar. Give the Laplacian a scalar, you first take the gradient, which moves you up to a vector. Then you take the divergence, which moves you back down to a scalar. So the Laplacian, whatever you give it, it spits out the same thing. You give it a tensor, the Laplacian of a tensor gives you a tensor. Laplacian of a gradient gives you a gradient. Curl also spits out the same thing. Curl of a vector field is going to give you a vector field. Anyway, this is just a brief aside. This might be useful to you as like a way to think about mathematical operations. It's useful here because it makes this equation a little bit less, it makes it make sense. Like, why are these differentials here? Well, they're here because you can't add stresses to forces. So what do? Well, you can add the divergence of a stress to a force because the divergence of a stress is a vector and force is a vector, and then we're just adding up vectors, and that's what we want to do. We want to add like things. Questions? These things in boxes, depending on which flavor of writing things down you like, are your equilibrium equations. Either this, or this. These are the equilibrium equations. This is one of the 4 sets of equations that we need to solve an elastic body. And really all we did was allow there to be some variation in our stress as we move in away from a point. And we took that variation to be, well, we know how to, we know that locally it should be the same as the initial value, plus some kind of expansion, a Taylor series expansion away from it by some small amount. Once we did that leap, then it was just a force balance like you've done 1,000 times. And then this stuff here, it was just all a way of saying, hey, I can see patterns here. This is a lot of equations. There's got to be a cleaner way to write this down. And by recognizing those patterns, you can either write it like this or write it like this. When I was starting learning this stuff, which wasn't until graduate school, I fully resisted all compact notation. I was just like, I need to write everything out explicitly in its things until it all made sense to me. And then I was like, oh yeah, okay, I guess I don't need to write out. Because sometimes you end up with like 9 equations that all kind of look pretty much the same. And so if this stuff is intimidating to you, that's fine. I mean, I wrote it like this forever. But I'm showing you this stuff because if you open up a textbook, or if you see something like COMSOL and you see, I'm going to load in the solid mechanics or the structural mechanics module, and I'm going to go and see what equation it's solving, it's not going to say this. it's gonna say, I can't remember what notation it uses, it's gonna say either this or this. And so if you are unfamiliar, have never seen that notation, even if you're not using it to do math, but you kind of are just knowing that like, all right, wait a minute, this thing connects me over to here. It'll be useful to you as you start to interact with these things, maybe in a finite element solver or in a textbook. So. All right, well, that's all I had for you today. Oh, actually, one last thing before you go. I have a meeting from 2 to 3, which is usually our office hours. So what I'm going to do is I'm going to do office hours from 1 to 2, and then normally, as I normally do, from 3 to 4 as well. So instead of 2 to 4 as my office hours today, it's going to be 1 to 2, and then 3 to 4. So thanks for your flexibility. All right, I'll see you on Thursday.